Hello everybody, welcome to my class. After being explained Hooke's law and elastic potential energy in the last two classes, let us now discuss what is work energy principle in elasticity and how does this concept apply to the problem solving areas. So in the work energy principle in elasticity, that is in the chapter Hooke's law, you can see this is a ceiling and one elastic string is hanging over here, and to the another end of this elastic string there is a weight, there is an object attached to here at this position A, whose mass is m, and due to the weight of or due to the acceleration of gravity, the string will go over here. That means it will be stressed up till position B, and where it rests under the action of the force W, that is weight, and due to this weight there is a tension T produced in the string. So when we talk up to the position B, so position B is the equilibrium position of this system when an object of mass m is attached and it has been extended to the position B, and this is in equilibrium state. Now what you can do here, that you apply an external force F and then let it go further within the elastic limit to position C, and then you can release. Once you have at this position, you can see that the object possesses mainly the three kinds of energy due to the weight and the force. Alright, and also you can see that there can be some other external agent that may affect this system, for example the air friction. So for this time we neglect air friction and any other kind of opposing forces. So first of all, we can see now we are interested to find the total energy at each position, and then we derive some term for the energy at that particular at those particular positions. So here in this case you can see that once the object is taken up till here within the elastic limit, then it is released. So you can say that with respect to this position C, we can check what sort of energies are stored here in this object at this position C. So in order to understand work energy principle in elasticity, you should have first the knowledge of Hooke's law, and also it includes the knowledge of resolving and composing the force, that the resolution and composition of the force, and also what is the potential energy and how it can be derived, what is the kinetic energy, how it can be derived, and those sorts of basic idea you require in order to go through work energy principle in elasticity. And now we check here that with reference to the point, reference to the position C, you can say that here at this point there is potential energy, kinetic energy, as well as the elastic potential energy due to the stretch in this string which is caused because of this weight and the force. So here if you check, then at this point you can say that kinetic energy equals to half m b square, alright, and half m times, you can see that at the beginning the velocity is 0 in this case, alright. So that this is, you can write here half m times 0 square is almost it is 0, that means there is no kinetic energy at this position C. And if you talk about the potential energy, and potential energy is given by the formula mgh means the potential energy is caused due to the position of the body. And here you can see that with respect to the point C, there is no position change. That means the displacement is 0 at this point. So that means displacement height is 0 at this point. So it is m times g times 0 equals to 0. So potential energy is also 0 at this point. Now let's check about the elastic potential energy. What happens about the elastic potential energy at this point? So at this point, if you talk about the elastic potential energy, that means this is caused due to the stress in the string by any deforming force. Here you can say it is W and F. So the formula in general is given by lambda x square by 2 times of original length, and here x square, you can see that x square means the total extension up till position C is x1 plus x2. So we replace x by x1 plus x2. So you can write here lambda x1 plus x2. That means we have to add up these two lengths together and then divided by 2 times of L, and therefore you can say that total sum of energy or total energy at C. In short, you can write also that T E and in the base C is in fact actually the sum of kinetic energy, potential energy and the elastic potential energy. And we have already seen that kinetic energy at this point is 0 and potential energy is also, you can see here, it is 0, but elastic potential energy is lambda x1 plus x2 square and divided by 2 times of L. That means L is the original length, you can see here, and then it is finally it is lambda x1 plus x2 square over 2L joule. Alright, so total energy at this point C is lambda x1 plus x2 square by 2L joule. So we see the total energy at this position C is lambda x1 plus x2 whole square by 2L joule. Alright, so we now have the total energy at C with reference to the position C itself. Now let's check that what will be the total energy at point P, which is between C and B. That means when the deforming force F is removed from here, that means when the body is released, the body will definitely go up due to the energy stored on this object. So we consider the motion of this body at some point P, where you can say that the body has velocity. You can say it is V or U, whatever you can say here, or you can say that V1 also. So let's say this velocity at this point is V1. So here you can see that this object has kinetic energy as well as potential energy. Kinetic energy because of the motion, and in that motion the body has velocity V1, and it has potential energy also at this position because of this distance, or you can call it is the state distance as displacement. And also there is elastic potential energy due to this sort of extension x1 plus up to this point. Alright, so let's check what will be the total energy at this point P. So we are talking about P. So at P, you can check that the kinetic energy, if you talk about, then kinetic energy formula is given as half m v square. So v we have supposed here as v1, so you can write here v1 square. And if you talk about the potential energy at this point, so potential energy is mgh. So let's check that. This is mg. What is the value of h at this point? So from C to P, you can see that this distance is x3. So potential energy is x3. And then what will be the elastic potential energy at this point? Elastic potential energy, if you talk at this point, is In general, you know that is lambda x squared by 2L, where x is the extension and L is the original length, and lambda is the modulus of elasticity, you know. And then it is lambda x square, means we have to check for the extension. So you can see here that up to here this is x1, alright, and up to here this is x2. So what you can do in this case, from x1 plus x2, and then this stress has been reduced by x3 at this position P, so you can write here minus x3. So extension at point P is in fact x1 plus x2 minus x3, and then as there is a square, so you can square it and divide it by 2 times of the original length, and therefore the total energy TE at P is, you can say that this is the sum of kinetic energy, potential energy, K means kinetic energy, P means potential energy, and then elastic potential energy, that is EPE. You should remember the short form, and then you put all these values. So we talk about the total sum of energy at position C as well as at position P with reference to the position C. Alright, and now you know that by law of conservation of energy, that means the energy is conserved, that means energy can neither be created nor it can be destroyed. That means the total energy at C will be equal to the total energy at P, and therefore you can write that by the law of conservation of energy, you can say that total energy at C equals to total energy at position P, and then plus x2 minus x3 whole square and divided by 2 times of L. Then what is the application of this sort of thing is that, for example, if you have known all these values but not any one of these values, then you will be able to find that unknown values based on the given value. And this is also possible that to check what would be the total energy at position B, at position A, and at any other position. So let's talk about at position B now. So here in this case, if you talk about the total energy at position B is the sum of kinetic energy, potential energy, as well as the elastic potential energy. Okay, and then you can see here that the kinetic energy at this point is, now suppose that at this point it has velocity v1, here at this position B you can say that the velocity is v2, then you can write here half m v square, that means v2 square, and potential energy you have to count the distance, so that distance is at position B, that is exactly x2 from here to here. This displacement is x2, so you can write here mg x2, and the potential energy and the elastic potential energy at this point is lambda extension square, so extension at this point is, so up to x2 extension is already vanished here, so now it has the extension at the equilibrium position B as x1, so you can write here lambda x1 squared by 2 times of the original length L. Alright, and similarly if you would like to find the total sum of energy at position A, for example, so A is exactly at the original length of this elastic string. So let's check here, say at this point the velocity is v3, for example, and the position that it shows that it is the sum x2 plus x1. So here in this case you can say it is kinetic energy plus potential energy plus elastic potential energy, and you have here kinetic energy as half mv square. V means at this point we have supposed it as v3, V3, so it is V3 square, and plus potential energy is mg and h in this case is up to here x2 and up to here x1, so total displacement in this case is x1 plus x2. And then you can see that the elastic potential is given by lambda times of extension, by 2 times of lambda times of extension squared by 2 times of L. So at this point you can see there is no extension, therefore you can write here 0, that means, and divided by 2L, that means there is no elastic potential energy at this position A because there is no extension, and hence the total energy at this point is half mv3 square and plus mg x1 plus x2 joule, right? And then what you think about by law of conservation of energy? So again, by the law of conservation of energy, here we talk about the mechanical energy, law of conservation of energy. You can say that the total energy at A equals to the total energy at B equals to the total energy at P equals to the total energy at C, where we have taken C as the main reference point in order to measure the energy at different points along this path. Alright, so it depends that how it is explained in the problem and what you need inside the problem in order to find the information that is being raised by the question based on the given information. Alright, so either you can take first and second, or second and third, third or fourth, first or fourth, first or third, as you require. And this is also possible that you have to note it here that like at this position, if you talk about the kinetic energy, so at this position kinetic energy is 0. If I am talking about kinetic energy, at this point it has some value, at B it has some more value, and if you go to the A where the extension ceased, at that point you will see that the value of B is maximum. That means the kinetic energy at this point is maximum. That means at this position A, when the kinetic energy is A, that will be the maximum value of the kinetic energy. But other sort of energy, for example here is the elastic potential, will have value just below this is minimum, or as you move from position C to outside, the elastic potential energy will have lesser value than the previous, and at point A it is almost 0 because there is no extension. Okay guys, there are a number of ways that we can see the total energy at different point in the elastic system. So here suppose that this is a 2 point where an elastic string is supported, alright, and it has some weight. If you attach here, then definitely it will fall down because of mg, because of this acceleration due to gravity. Its position will be here and this position will be in the equilibrium state after some distance ma. And then what you can do here, that you apply a force F and stretch this string further from this equilibrium position to position B, and in that case we'll check what would be the total energy at each point. Alright, so here in this case you can see that like in the equilibrium position and about this stretched point, so you take the reference as point B. So when you take the point B as reference point, then at this point B, let's say that at point B, the total sum of energy at point B is, in fact it is kinetic energy plus potential energy plus elastic potential energy. Alright, so kinetic energy at this point, you say that the velocity is 0 in the beginning and there is no position change, therefore there will be no potential energy. So that you can write here, it is half m v square and plus potential energy is mgh, and then it is elastic potential energy is lambda x square by 2 times of the original length, and then it is half m v square, means there is no velocity in the beginning. Initially there is no velocity, that means it is 0. So body is at rest at this point before releasing this, and then mg times of 0, because there is no position has been described here. If you are talking of the potential energy with respect to the position b itself, and then lambda x square, then we have to find the extension, the string from both sides, and then that sort of extra length, then the original length will be the extension. So we can write here in general e square by 2 times of l. E square means we have to find what is the extension at this point. So we saw at point B, alright, at point B is that the total sum of energy is only, this is lambda extension square by 2 times of L. Now let's talk about the total energy at point W. What happens at point W? No, it's W means weight over here. You can say at point W also, but as we have already taken A, so we can write here at point A. So here also you have to check for the kinetic energy plus potential energy plus elastic potential energy, and sometimes you will be given some sort of other form of energy due to the other factors here, for example the frictional force or any other kind of external force given. So here we talk about the system works under the frictionless condition. So kinetic energy, you can say that definitely at this point its velocity is going to be v, for example, or you can say it is v1 as you like. So in fact there will be some value of the velocity in this case, therefore there will be the kinetic energy also. So you can write here half m v square, because velocity is v at this point, and it does have potential energy also because the displacement has been changed here. So potential energy is this distance, so potential energy is mg, and h means at this point either you can calculate by the given condition, otherwise you can say in general at this time is that length is AB. Alright, so this is the potential energy, and let's check if there is elastic potential energy also. Yes, because due to the weight of this body as it is in the equilibrium state at this point, there is some extension here. So you can write here that lambda times of x square, means you can say that it is e dashed square, that means extension at B and extension at C, there will be not the same value, there will be the different value that we need to calculate it. We'll see very soon while solving the problem related to this sort of thing. So this is lambda e dash square by 2 times of the original length. So note that always in the denominator there is 2 times of the original length, and again you can apply again by law of conservation of energy. You can say that total energy at A equals to the total energy at B. Okay, and this is also possible that you should be able to find the total sum of energy at any point between M and B. So for example here also, so at this time I am taking at this point. So what you think about at point M? So what I am going to talk about that the total energy at M in fact it's also be going to be equal to the total energy at other points. So here in this case you can say that the total energy at M, I am talking of this M position, you can see that the velocity will be maximum at this point because the string has no extension or very low extension. So in this case we have no extension in the this string because we have taken this to be original length. So total energy, if you are talking at this point M, then that's going to be half M V square, or you can say at this point its velocity is V dashed or V2 or anything you can suppose different than the value of velocity at position A. And the potential energy, if you talk about, it has total distance traveled as B to M, so you can write BM, or sometimes it is given or sometimes you need to calculate this distance. So at this point we generalize in terms of ABC. So M G H means you can call here at this point that is BM or MB. So this is the potential energy. And then what about the elastic potential energy at this point? You know that the string is not stretched at this point. That means there is no elastic potential energy because there is no extension. Extension is 0. So elastic potential energy at this point will be 0. So this is the main idea, that how to get the relation between the energy from one point to another point in this sort of given system. So this is the idea, that how we develop the relations between different points along the motion of the object in the elasticity system. Alright, and by using this sort of relations we'll be able to solve a lot of problem that includes work energy principle. So let's now apply this work energy principle that we have just learned and discussed earlier to the problem area. Alright, so here you can see this figure and just read out this question first of all and then see what are given and what we need to find. So here you can see it says that a particle of mass 0.35 kg is attached to the midpoint of a light elastic string of natural length 4 meter. The ends of the string are attached to fixed points A and B, which are 4.8 meter apart at the same horizontal level. P hangs in equilibrium at a point 0.7 meter vertically below the midpoint M of AB. You can see the diagram. And then find the tension in the string, and hence show that the modulus of elasticity of the string is 25 Newton. So it has been taken from the past paper and it carries the marks 4 for this question number 1. And now on another time it says that P is now held at rest at a point 1 meter vertically below M. 1.8 meter vertically below M, and is then released. Find the speed with which P passes through this point M. So here you can see in this figure distance between A and B is given as 4.8 meter, but you can see that the natural length is only 4 meters. So even though if P is at M, there is still extension in this string, because a string has length 4 meter only, original length, but this sort of distance where the string is stretched by is 4.8 meter. Therefore there is an extension in the string at this point M also. So let's first talk about the question first. Find the tension in the string. Tension in the string means obviously the tension will have, this is T here, and also in this way you can see that it has tension at this point, and the modulus of elasticity that you have to find in the string as 25. So in this case we have to resolve the force first of all. So let me check is that here this is the midpoint and the whole thing AB is 4.8. that means this distance is going to be divided by 2, then it is 2.4 meter, and then we have obtained this length and this length also. And with respect to this angle, if you talk about, MP is base and MB is the perpendicular. So if you use tan theta, so theta is here, you can say that this is angle MPB, that is going to be P by B, and P value you can see that this is 2.4 and B value is, it is 0.7 meter given, so over 0.7. and now go to the calculator, you can write it is 2.4, then divide by 0.7, and this value is going, so it is 73.74 degrees. Now we have got the value of this angle, which is 73.74 degrees. Now we resolve this force, given force T. So in this case, let's take this as a baseline. So in that way, if you are taking this way, and for this tension, which both the tension are equal in this case, in this equilibrium position, because this is the same material here, and then this way if you resolve one of this tension over here, so this is going to be T cos 73 point, it is going to be 73.74 degrees, alright, in this way. And its another component will be perpendicular to this point, and this sort of thing is going to be T sine 73.74 degrees. And what happens if you resolve from this side, because you know that this is the midpoint and it is perpendicular, so these two lines geometrically must be equal, and the value of tension is also equal in each part of this string because of the same material over here. So in that case also, along this way, the component for the force T will be T cos 73.74 degrees. So you can just put here 2, so it's going to be 2 means again it is T cos 73.74, so you have to add the same value, therefore we can write 2 times of this. And its another component which is perpendicular to this line will be along this way, so that will be T sine of 73.74 degrees. So in the equilibrium state, you can see that these two forces are opposite to each other, so they cancel each other, alright. And then what you can use here, this value, in order to find the tension in this string. So along this way and towards the downward, what you can see here, downward, the weight acts downward because of the acceleration due to gravity, so its mass is given as, you can see here, the mass is given as what it is, yes, 0.35, so it is 0.35, and G means you can write here 10, so weight is in fact it is 3.5 Newton. And you can see that as T sine 73.74 degrees towards left and towards right, they balance each other, so they cancel each other. Then these two forces, that means the W and 2 times of T cos 73.74 degrees will balance each other. So in this equilibrium condition, you can see that 2 cos 73.74 degrees equals to the weight of the body, which is 3.5 Newton. Alright, not 2 only, that is 2T. Okay, so therefore you transpose everything towards right side, that means you divide both sides by 2 cos 73.74 degrees, then you will have the value 3.5 over 2 cos 73.74 degrees. Let's go back to the calculator and calculate this value. Then over here, and then finally it is 6.25 Newton. Okay, yes. Now question is asking you to find the tension in the string that we have already got, that is 6.25 Newton, and now you are to prove that modulus of elasticity of the string is 25 Newton. So in this case we have to work a bit more, and now you can say that this length as L dashed, that means the extended length as L dashed. So suppose, or let the length that is PB is L dashed, that contains the original length L plus the extension the string. So here we'll take only one part of the string, because from either side, either this part or another part, that means we take the extension in the half of the original length, and that will be X. So first of all, firstly we need to find the value of PB, that is the extended length over here. So value of PB, in order to find the value of PB, what you have to do, use again the trigonometry over here. So you can you know that sine of any angle is P by H, or cos of that angle is B by S. So either you use sine or cos, you will get the value of PB. So let me use cos. So you can say here cos 73.74 degrees, that means we are talking of this angle, and then it is defined as B by H, and you see that B in this case is given as, already given for this angle, MP is the base, and that is given as 0.7, and then H value we don't know, that we need to find. So H in this case, S means we have PB, that means we have support that as L dash, or you can write PB also, no problem. So this is L dash equals to, if you transpose this to the left, that is S means L dash we have supposed, and then this is 0.7, and then by cross multiplication, if you transpose to the another side, it is going to be cos 73.74 degrees. You can go again to the calculator. So now by Hooke's law, you know that T equals to lambda x by L, and here although we have 2 times of T along this way, because it has effect for this part of T and this part of T also, that's why we have taken everything over here. But in order to find the value of lambda, we say that T equal to this, so you take either T from right side or T from left side, both will work. So here I am taking the T from one side only. So here you can say that the value of T that we have already obtained is, you can see here, this is 6.25, so you can write here 6.25 equals to lambda x. So it is, lambda is, how much it is, we don't know, we have to find, an x value is, we have 0.5, and the original length, instead of L, now it is L by 2, because we are taking it from half of this original length only. Alright, so you can write here, in place of L, you can write here L by 2. So it is here L by 2 means it is 4 by 2, and then you have here lambda means it is lambda times 0.5 means 1 by 2, and this is 4 means 4 by 2 means 1 by 2, or the way you like, it is easy for you to calculate. You can do that way also, in the way you feel it easy, and then half and half have been cancelled out. So we have now lambda by 4. Now from first and last, if you cross multiply, then it's going to be lambda equals to 4 times of 6.25, and 4 times of 6.25 is, in fact, if you multiply, it is 25, and then this is Newton. Now let's check back to the question. Question says that find the tension in the string, that we have already here, 6.25, and hence show that the modulus of elasticity of the string is 25 Newton. So this is proved that we have to show. Now let's talk about the another part of this question. It says that P is now held at a point 1.8 meter vertically below M, that means somewhere here vertically below M, and is then released. Find the speed with which P passes through M. So you have to, in this situation, you have to find the speed of the particle at position M. So here we apply the work energy principle that we have learned. So in order to do that, first of all, let's display the situation over here. So it should be just below M, means somewhere here, alright, and then about this you can add this point. Okay, so you can say that this particle is now over here by a force F, you can say. That means the question said that P is now held at rest at a point 1 meter M, 1.8 meter vertically below M. That means there must be some extra force other than the weight W has been applied here. That is, in addition to the weight W, there is some external force over here. That's why its position is P. You can say this position as P dashed now, or you can name anything for this position. So I am calling it as P dashed. Okay, so another position is P dashed, and find the speed with which. So that means you have to calculate the energy at P dashed and also the energy at M, and we can also find the energy at P, but according to the question we don't require the energy at P. So now let's check what happens in this situation. So now our triangle is A, P dashed and B, and now you join over here because this is just vertically below this point. Now you have this length is, again it is midpoint of AB, and AB is 4.8 meter, that means it is 2.4 meter. Alright, so we have got this distance is 4.8 meter, and below M it is telling that this distance is 1.8 meter up to here. So if you say this is the position of M and then this is the position of P dashed, that means this position I am talking of. Alright, T. Now we'll forget this 0.7. We'll now remember 1.8 from M to P dashed, because we have to relate the positions P dashed and M. So with reference to point P dashed, we check for the total energy here. So before we check for the total energy, we have to find the extension in the string, and firstly we consider only this part of this string. So first of all we find this length by using the geometrical condition here now. So if I am taking tan of angle P dashed, here M P dashed B, you can say angle M P dashed B equals to, you know that tan theta equal to P by B, and for this angle you can say that the perpendicular is MB and the base is MP dashed. So MB value is here 2.4, alright, and B value is not, it is 0.7, now it is 1.8, and therefore your angle MP dash B is going to be equal to tan inverse of 2.4. You can say it is 24 by 18 also, because decimal will be cancelled out, divided by 18. And now let's go again, and then you can see here that this value is 2.999, and it goes on and on like this with some other decimal values over here. So this is nearly equal to 3. So extended length along this way is 3, and half of you can say that the original length is 2 over here. Therefore in this case the extension x, if you say, or x double dash, you can say extension x double dash along this way, and it is going to be now 3 minus 2 if you are considering along one side only, and that is going to be 1 meter along one side, either to the right side or for the length of P dash B, or it is the length of P dash A. But in this case there is influence of the tensions from both the sides. Therefore we take the entire length, entire extension in the entire length AP dash and P dash B. So therefore the actual extension in this case is 2 times of x dash, we can say x double dash, and 2 times of x double dash is x double dash we have obtained is 1 meter. That means it is 2 meter, nearly it is 2 meters. So the total extension in this string at this when P is at the position P dash. Alright, and now we check for the energy at each point here. So according to the question we have to find the speed at point M. That means we take the reference of point P dash and M only. So we can say again, with reference to the position P dash, so total sum of energy at position P dash, that means over here it is kinetic energy, potential energy plus elastic potential energy. So let's check for what is the kinetic energy at this point. So you can say that in the beginning the velocity is 0, therefore kinetic energy at this point is 0, and also with reference to the point P dash there is no position shown with respect to P dash itself. Therefore at P dash the potential energy is also 0, but the elastic potential energy is given by lambda x squared by 2L, that is the original length. And we have just seen that the value of lambda is 25 Newton. It is also asked to show that it is 25 Newton, so it's already here now. So it is 25 times x squared, that means the total extension in the string is now it is 2 meter nearly, and this is 2 times of original length is 4, and then we cancel this 2 and 2, and total energy at this point is going to be lambda x square, sorry, x square means it is a square, and then it is 2, so 2 square and 4 will be cancelled out in fact, and then you will be left with 25 by 2, and that is going to be 12.5 joule at this point. Okay, and at M, you can suppose at M if you would like to find the total energy. So total energy at M, you can see it is the sum of kinetic energy plus and potential energy and the elastic potential energy in this at this point. This is also possible that there might be some frictional force due to air or due to some other agents, and those things have been neglected at this point, so we will not consider any other external opposing agent over here. So now the total energy at M is kinetic energy. You can say it is half mv square. M value is already here. You can see that this is 0.35. So you can write here 0.35, and then it is v square, means suppose that the velocity of the particle here is v. You can see that along this motion the v will be maximum at this point. So mv square, and we don't know this v value, so we write here 0.35 v square. And let's check for the potential energy at this point. So potential energy mgh, so m is again here 0.35, g means you know that g is 10, and h means the whole distance from p dash to m, which is 1.8. This is 1.8. And what about the elastic potential energy at this point? If you talk about the elastic potential at this point, so you can see that here what will be the extension in the string. So the string has original length only 4 meter, but it has been tied from A to B, which is in fact 4.8 meter. That means there is an extension of 0.8 meter. So what you can say directly here, you don't need to calculate it extra because it is obvious from the figure over here. And then elastic potential energy is going to be lambda value is 25, and x square in this case is 0.8 square, and this is 2 times of original length is 4 meter. Now let's take the calculator and let's have this value, or let's have this term in the simplified. So we have calculated that total energy at position P dash is 12.5 joule, and the total energy at position M is this, and therefore by the law of conservation of energy, you can say that total energy at point P dash equals to total energy at point M, and then here total energy at point P dash is, we have here it is 12.5 Newton equals to total energy at M. You can see that here 0.175 v square plus it is 8.3, it is 8.3. So it said that find the speed with which P passes through M. So by using this relation through the work energy principle, we will be able to find the velocity at this point M. Now solve it. You can write here 24. Now again go to the calculator and find the root of that answer. So this is the square root of the answer, which is 24, and then equal, it is 4.898979. you can see here. So nearly you can write 4.90. So it is nearly equal to 4.90 meter per second. So this way we found the value of B at M, and here we have the speed V equals to V of P that when it passes through M is 4.90 meter per second, and this is the answer. Okay guys, I'm sure you are now able to do almost all sums from the chapter of Hooke's law, which are given in 3 parts, that the Hooke's law principle, and then elastic potential, and lastly it was the work energy principle in elasticity. So if you have learnt all these 3 things, then I'm sure you will be able to do almost all problems from the book exercise as well as from the CIE past papers. So that's all for now, and thank you for your patience.